In exploratory data analysis, we understand data primarily visually, okay, to identify the underlying structure, patterns of a particular variable, and the relationship of different features with the primary target variables to see how each feature is impacting target variable. And it is an integral part of machine learning. Why? Because first of all, it helps in feature selection. Okay, through this visual insights we understand what are relevant features, which features are impacting the target variable and are likely to be part of predictive modeling. The other is it will further help in guiding us to data cleaning or pre-processing part, where we will know what values are having outliers, let's say the way data is distributed, where we need to normalize the data. So overall EDA serves as a critical step. Okay, here as part of EDA we will be making use of different kind of graphs, including the ones which we have already learned, right, like histogram, scatter plots, line plots, correlation heat map. But the important point here is when to use which chart. We are utilizing data to come up with a storytelling. How do we tell the story? Through which graphs? There are so many graphs, and which to use when. That aspect also we will be looking over here. So friends, let's start by univariate analysis. So as the name says, univariate, related to just one variable analysis. And what could we be interested in univariate is primarily its distribution, whether it has outliers or not, or in case of categorical variables, which value have more influence on target variable. So first let's have a look at the distribution of target variable. We have already given dot describe, right, and we have already interpreted what dot describe is describing. So let's create a visualization with the help of plt dot figure, and within that I can give fig size. It will create a blank figure, and then we can create subplots within that. To create subplots, what we have to use is subplot function, where we can specify how many rows, how many columns are there, and what is the number of figure which we are going to visualize over here in the grid. And similarly we can create another subplot over here. So in first figure what I want is hist plot. I will specify which variable I want on x-axis, which is the data this figure is going to use. I can also specify KDE is equal to true to check out this distribution, smooth distribution. And similarly in my second subplot I can define box plot. I can provide the title, let's see what it generates. So I have this figure, right? And as we can see, for the same variable we are looking from two aspects. We already looked at one aspect through textual information, and we could see that through this textual information that the minimum value was 0 and the median was 504. We could also interpret from here that median is less than mean. What does that mean over here in the figure? So let's say our median value is 504 and maximum value is 3556, which is this figure indicates that. But what does that mean? That very less rented bike count numbers are lying in this category, right? And most of half of the values are lying over here below median, right? Mean is somewhere around 700, which means that mean is shifted towards outliers. Mean is a parameter which gets influenced by outliers, right? This whole story indicates that it is a positively skewed distribution. Positively skewed or right skewed means that the tail elongates towards the right side. This whole story which histogram is telling can be read from box plot as well, the construction of which is based around the quartiles. Quartiles means 1/4, where we are dividing the whole data set into 4 equal parts. And the median represents the second quartile. This one is 25% quartile and this one is 75% quartile. And this whole box indicates the 50% of data. This distance from Q1 to Q3 is called IQR or interquartile range, and it determines how farthest the whiskers would lie, which are 1.5 times below or above the IQR. Any point lying beyond these whiskers is outlier. Now, the presence of outliers on both the sides, even presence on both the sides, would indicate normal distribution. But since the outliers are already lying on the right side, which is also shown by a histogram, it indicates the positively skewed distribution, which is also confirmed by the off-center median. Had it been a normal distribution, this median would have lied over here. Other point to note is that this is completely 50% data. That means rented by count majorly are lying between the value indicated by this to this. Half of the values are lying below this. And that is how we read boxplot. Again, why we are analyzing this over here is because we want to see if this data distribution is appropriate for machine learning modeling. Machine learning modeling is heavily influenced by outliers and the distribution. It assumes that most of the model assume that the distribution is normal. And during the data pre-processing part, we will be doing the transformation and outlier treatment. Let's say an example how we will be doing transformation, which we will not be doing over here. We will be just looking at how transformation will transform the distribution, and that we can do with the help of, let's again draw a plot, hist plot, and to that what I will pass a mathematical operation on all the values of our variable of interest, which is rented by count. And if I run this, you see the same distribution has converted to almost normal distribution with the help of square root function from NumPy, and this is called square root transformation. Then there can be other kinds of transformation. The other one of which is log transformation, which again implies that we are applying log on individual values of rendered by count and then creating this plot, and see this will. So while doing data pre-processing, we need to check which transformation works better to normalize the distribution, and we will be picking that distribution. Again, for outlier treatment, we will be using some methods which we will look at in data pre-processing part. For now, let's move to see the distribution of other numeric variables as well. To see distribution of other numeric variables, we will create a figure which is like canvas using subplots, and where we will be defining the grid already with the help of fig axis equal to plt dot subplots, and there we will be allocating how many rows we need and how many columns we need, and this is purely based on the number of numeric columns we have. We can do it dynamically also by assigning the list length and all, and then defining how many columns and rows we want, but I don't want to complicate it at that level. I'm sure we can do it when we need it. Axis dot flatten. What is this doing? Flatten methods. So if you see, axis is a 2D array, right? Array inside array, and we are converting it into a flattened array. What does that mean? That it will be a 1D array with the values in the same order. Okay, and why we are doing? So that we can run it through for loop. Let's see how. So right now we have created these 3 into 4, which is 12 subplots, and we intend to fill all these with the numeric columns. So to continue, what we will do, for I comma var in, and we will be accessing the list of num columns which we have already created, right, which is basically the list of numeric columns, and for each we want to create hist plot by supplying that particular var, which is the column name, right, which is storing the column name, and in axis we will pass the axis index, which we are picking from again the number of the column, the index of the column. Okay, then we can also supply the data which this plot needs to access, and we know KDE is equal to true to indicate the distribution, smoothened distribution. Let's run it. So we have these, right? One thing which we can do is over here is, I don't want to print axis now. What we can do over here is plt.tight layout. So what this tight layout will do, it will adjust all the figures within this, maintaining proper space, so that we can see properly what are the variables. Okay, we have some empty figures which we can turn off, or maybe we do some extra. For now, what we can do is we can simply say axis -1 dot axis off. Okay, and similarly for last second, and similarly for last third also we want to turn off them. If we would have dynamically retrieved, we would not have faced this problem. Now let's have a look at the distribution of these variables. Rented by count, as we already know, is positively skewed. Temperature almost seems like normally distributed, and humidity too. Wind speed again looks like positively skewed, and visibility, dew point temperature looks like almost normal distributed, while visibility looks like left skewed or negatively skewed. Let's have a look at the visibility parameters, which is this here, and if we look at the mean over here is less than the median. Okay, this is the thing which is indicating again that mean is shifted towards left side, and the outliers might lie towards the left side, and as is the tail, and this is the indicator of left skewed distribution. So we will be coming back to these and addressing these again during data pre-processing. For now, let's go to bivariate analysis, which is at a time we are analyzing two variables. That means relationship of one variable with other, and what we are primarily interested is in the relationship of a particular feature with the target variable. So the first purpose in bivariate analysis is analyzing the relationship of target variable with the variables. Okay, so we can divide it into two parts: relationship with the categorical variable and then with numerical variable, to see the influence of each. Now when we come to categorical variables, how we can check the influence is through boxplot and bar plot. So let's see how. So again, we have multiple variables, so we will be drawing subplots over here. And first we will check the influence through boxplot. And to check the influence through boxplot, for each categorical column, what I'll give sns dot boxplot, and in the x I will supply the column which is each categorical variable, and in the y I will give the target variable, again data, and the axis using the index. Alright, let's run this. So we see these values. So let's have a closer look at what each is indicating. So this is hour-wise distribution, and we have drawn box plot for each hour, and similarly for each categorical value belonging to a category, we are looking at where is the maximum spread and where the minimum and maximum value or medium is lying. For example, if we look at summer in seasons, right, we can easily see that the rented bike count is higher in summers as compared to other seasons. Median is above all the medians. Variability is almost same as that of spring, but the values are higher. Similarly, if we see R, we can clearly see that the rented bike count is higher in these hours. Let's see another example. Now there's a problem here. These values are mixing because this axis cannot accommodate all the values. What we can do is we can rotate these values to make it better readable. For that, what we can do, for each subplot params method and in tick params method, on axis of x we can give rotation is equal to say 45. Let's see what it shows. So here we can clearly see now it has become readable with the help of tick params. So that is how we see in box plot the insights across different categories and the spread and the median central tendency with the help of this. Apart from box plot, we can use other ways like visualizing average rented bike count across all the categories using bar plot. Let's see an example how we do that. First, I will take an example of grouping function. So we will use df.groupby function and we will group by on the basis of particular column, let's say seasons. We have 4 values in seasons, which is winter, summer, spring and autumn, and it will group all the values belonging to particular categorical values. And let's say we derive from that rented bike count, then we apply aggregation function on it. So aggregation function can be sum, mean, right? So what we are doing, we are deriving particular categorical value, all the values of rented bike count, and then we are applying aggregation function, let's say mean on it. Okay, let's see what we will get. We will get a get data frame. If I do dot reset underscore index, I'll get a something like this where I have a data frame with 2 columns, season and corresponding average rented bike count. Now doesn't this look useful? Right? We can directly do comparison of average bike count across different categorical values of seasons, right? Let's make use of this across different values of each categorical variable. And what we can do, we can simply use this over here, and instead of seasons we can pass the each column over here. Let's create a variable name by group bike count grouped equal to, then it's simple like we did for box plot. We can do bar plot where we can pass in X the column name and in Y we can pass rented bike count. In data we can pass, instead of df we can pass our new data frame created particularly for this visualization, and then of course we need to pass the axis. Ax is equal to axis I. Right, let's run this. And of course we have this problem, and I can directly copy paste because we earlier saw this problem of rotating the ticks. This seems helpful because we are comparing the average bike count across each values of categorical variable, and we can clearly see that during summer average rented bike count is high. It is higher on no holidays. It is higher during the period between 5 to 7 and during the morning hours of let's say 7 to 9, which seems obvious because these are peak hours in the morning and evening. Functioning day, it's interesting that it has only one value, and we even may need to drop this variable because since it has only one value, it is not helping in predictions, right? And there are only 2 values of years, we may drop them. And we can also see that during these months, June, July, May, these values are higher, and similarly during these months, right? And they may correspond to this May, June, July may correspond to the summer season, right? So these are in sync. And again we see that there is no effect of in general the day of the week. So this is how we can analyze the impact of categorical variable on the target variable. One interesting plot which I would like to show you is related to this R. Okay, it's a line plot. When we want to see the trending in terms of time, right, we make use of line plot, and let's see how it helps us. So to make line plot, what I have to do, I have to create SNS dot I can either give SNS line plot or point plot. It's simple, right? X is equal to, on x-axis I want R, and on y-axis I want rented by count, and our data is of course TF. Let's run this, and we can see this is slightly more helpful when the factor is time. So these are specific hours, it could be continuous time steps. We can see the trend through line plot when especially it is time, and with the help of point plot we are able to make out a specific, we can jot the corresponding hours with the help of point, and it may be needed or not needed depending on the need of storytelling or analysis. This Y label is wrong over here. Before we leave bivariate analysis for categorical variables with the target variable and head to numerical variables relationship with rented by count, let's talk about one of the data pre-processing steps which we will be doing for categorical variables, and that is categorical encoding. If we notice, the categorical values are either strings or numbers, or some numbers have no significance in terms of magnitude, right? While R has significance, but 2017, 2018 doesn't make the year, one year bigger than the other. The whole point is this: machine learning model will not accept anything which is non-numerical in nature. Then we also need to encode the values which even are numerical in nature but hold no significance, and ultimately as part of categorical encoding in data pre-processing we will be converting all the values to relevant numerical values so that we can feed it to machine learning model, and that will be the part of data pre-processing. And let's wait for that and head to relationship between the target variable with numerical variables. When we talk about the relationship of target variable with, which is again a numeric variable with a numeric variable, the first plot which comes to mind is a scatter plot. So we will be drawing that. To draw a scatter plot, we can give SNS dot scatter plot. X is equal to the name of the column which belongs to numerical column. Y is equal to rented by count. X is the one of the index column. Let's run this. We have forgot to pass data. Alright, so let's have a look at these values. These scatter plots, so we can draw some conclusion, but not to that extent because the relationships are not that clear. Maybe line plot would have helped over here more, but we can see if that temperature increases with the rented by count increases with temperature, and let's see the rainfall specifically, which is obviously for no rainfall, which is 0, the rented by count would be higher, and as the rainfall increases, number of bikes rented would decrease definitely. Let's do one thing. Let's modify this plot from scatter plot to reg plot. What it will do, it will draw the line which will identify the relationship between this lines, and will come up with the best fit line, give color to that line. So if you see, it indicates kind of relationship which it can work out from these scatter plots. Seaborn can work out from these scatter plot points, and temperature has positive relationship, humidity has negative, wind speed has positive relationship, and so on and so forth as the line indicates. Let's dig deeper now with the help of next level of analysis called multivariate analysis, where we will be having a look to proceed further closer to data pre-processing by identifying correlation between these variables, and we will also identify multicollinearity. Multivariate analysis, of course, is analysis which includes more than 2 variables. So let's see one by one. As an example of multivariate analysis, we can take this example, SNS dot line plot, which we already drew for R, right? X is equal to R and Y is equal to rented by count. We can give another parameter over here as part of multivariate analysis, which can be another variable in terms of which we want to see the variation. Let's say seasons, okay? And let's run this and see what it provides us with. So if you see over here, we have a legend set that winter is for blue and spring. So again, it has given us a trend in terms of R, but it has given for each season. So this is an example of multivariate analysis where we have three variables in play together, right? More than two variables. And with the help of hue parameter, what we are able to do is we are able to segregate each of the trends of R with rented by count based on each season, and this is very useful, which we will be using again and again. Before we proceed to correlation heat map, next multivariate analysis method, let's just see one more thing. So df num underscore call, which are numerical columns, and we apply a correlation method to it with respect to rented by count. Let's display it. We can also sort these values in particular order, ascending, descending, equal to true. Okay, let's see. So if you see over here, let's make it false. Okay, if you see over here, rented by count is of course in perfect relationship with itself, and temperature was the one which we observed, which was having higher positive correlation, and then came dew point temperature, solar radiation, and so on, with humidity with the closest negative relationship, while wind and rainfall were in the middle. So what does it mean? That correlation varies from +1 to -1, where the plus sign indicates the positive correlation and minus sign negative, and higher the magnitude, closer to the 1 magnitude on either side, represents highest strength of relationship. Now let's proceed to heat map. To draw heat map, let's draw a correlation between all the variables, which is basically multivariate analysis, right? So we will do same thing, but we will not pass rented by count this time. And to this we will draw a heat map using SNS heat map, and to this heat map we'll pass the scope core_1. Let's see. So we come up with this colorful heat map where the scale can indicate the strength of relationship. If the value is closer to 1, it is lighter in shade. If it is very dark in color, it is closer to -1, and these between values are of lower strength. Alright. With the help of correlation heat map, we can visually represent the strength and direction of relationship between numerical variables in the data set, and it uses color coding to indicate the correlation coefficient. And let's make it better with the help of annote is equal to true. Yep, you can change the color, and there are many other arguments. Let's just keep it simple. Now we have the value of the correlation coefficients. If we have a look at it closer, 1 means the relation of variable with itself, and of course it needs to be perfectly 1. And if you see 0.91 is very high, so it means temperature is very highly correlated to some dew point temperature, right? Similarly, we have this 0.54 relationship between temperature and rented by count, and if we see the negative relationship between visibility and humidity, it is also towards dark, and so shows the higher strength of relationship. One particular point coming out from this heat map is this 0.91. That means this temperature and dew point temperature are very highly correlated to each other, and that is a sign of multicollinearity. What is multicollinearity? Multicollinearity refers to a situation, okay, where 2 or more predictor variables are highly correlated, which we can see over here. And this means that one predictor variables, right? Of course, we are looking for higher correlation with the target variable, which is another case. But in the case where we will be doing data pre-processing and feature selection as part of that, we need to see if two features are multicollinearity related, that is highly correlated. That means that one of the predictor variable can be linearly predicted from other variable with a substantial degree of accuracy, and it can pose issues in prediction right? It may come up with false estimates, false interpretations. We need to remove it. All right, so we need to drop one of the variable over here. If we look at this closely, this multicollinear dew point temperature is also highly related to humidity. Humidity is not related that much to temperature. So what we can do, we can, as part of pre-processing, we can choose to drop this dew point temperature, and this is our conclusion over here. So as part of this tutorial, we are done with exploratory data analysis, and with the help of EDA, we have already identified that before going to machine learning modeling, we need to treat our data to make it suitable for ML modeling. There are outliers, there are categorical variables, and we need to normalize the skew distribution, coarse train test spread, which we have been doing, and then scaling down of data. And then we need to select suitable features which can go as a right choice of predictor variable to follow up with machine learning modeling.